So we know the basic shape of the normal distribution now, and we've seen that it occurs a lot in nature. So there are so many different things that we could measure, and each one would have its own curve or normal distribution. And it would be really helpful if we could find the area underneath the curve in any of those cases, because the area under the curve for a particular range of values gives us the probability of any score in that range actually occurring. Now, there's two big problems. The first problem is that if you've got some function, it can be hard to find the exact equation of that probability density function. And then once you have that equation, it can be really hard to integrate it. So these problems are basically solved by comparing all the normal distributions that could ever exist in the world with one gold standard distribution, which we call the standard normal distribution. And we compare all of the other normal distributions to this special one by using what we call z-scores. So let's have a look at some of the features of this standard normal distribution. Now it's called a function of z, and so instead of using f of z, we use this notation here to denote the standard normal distribution. And we have z on the horizontal axis instead of x, because what we're actually referring to here are z-scores. Now, what is a z-score? Well, a z-score talks about how many standard deviations any score is from the mean. And so the nice thing about this standard normal distribution is that the mean is exactly 0. And that makes this an even function. And it means that we get this symmetry on one side of the vertical axis and the other. Now, the area under the curve equals 1, so it is a probability density function. The other thing that we need to note is that it is always positive too, so those are the two criteria for it to be a probability density function. And the standard deviation is exactly 1. Now, you'll notice something else that happens at exactly 1. What we get is a point of inflection on both sides at exactly 1 and minus 1. And that's not a coincidence. This curve is sort of built that way. So something special happens one standard deviation away from the mean, it stops curving this way, and the concavity of the curve actually changes. So we've got a standard deviation of 1, and of course that means that the variance, which is the standard deviation squared, must also be 1. We've got our mean right in the centre, making it an even function. And now we can basically look at any value of z and reason how many standard deviations it is from the mean. So if I look at a score here where z equals 2, I can say that this score is 2 standard deviations above the mean. A score down here of minus 3 is 3 standard deviations below the mean. A score here at minus 1 is 1 standard deviation below the mean. That feature that makes this normal distribution so easy to use. Each number is actually a number of standard deviations away from the mean. Now, when we're dealing with the standard normal distribution, we're generally looking at the PDF, and we're thinking about what the area is under the curve in various regions. We can't find, remember, the probability of any one event occurring, but we can find the probability that a score is in a particular range. Now, the CDF would look like this. You're not going to see it a whole lot in this course, but considering that we've just looked at how we can use these two types of graph together, it's a good idea to consider this now. Now, the CDF has different notation. This is lowercase phi, the Greek letter, and it's got its sort of stalk through the center of the circle at an angle. It's quite confusing, I think, that uppercase phi looks very similar. It's got that vertical one and it's drawn more like this. So that's like before when we were using little f and big F, I suppose, same sort of idea. Now the scale is going to be very different. The scale of this graph is around about 0.4. It's not exact, but just gives you some rough idea of how tall it is. Whereas on the CDF, we know that the probabilities add to 1 because it's adding them up as we go. So as we get further and further across the distribution, we arrive at a certainty. Now with this type of graph, we've got tails that head off into asymptotes. And so that you can see here over on the CDF, this line might approach here and go on for a fair way, being almost virtually impossible, but still vaguely possible. So these lines will approach each other here and here rather than necessarily actually meeting. unless there's a reason to do with the data that means that you can't have a value that's further out. Now, if we wanted to see the halfway value of the distribution, this graph makes it so easy. Because of the symmetry, this is the mean, but we can see it's also the median. And that's because half the scores are on each side. So it makes complete sense to have the middle of the distribution by both median and mean right here. It's also the mode because it's the most common occurrence. Now, if you wanted to find the middle of the distribution using the CDF, you need to look for the place where the probability is half. And it makes sense that similarly, it's right here at the 0. And so that's why it's going through half here, because half of the scores are on this side and half are on this side, exactly the same as what we've got here. Now, if you wanted to find things like, say, percentiles, we've got two different strategies. One is that we can say, all right, if we want to say, where's the 90th percentile? Which Z-score is showing us the 90th percentile? The strategy here with the probability density function would be to say, show me a Z-score whereby I can put a line and shade everything on this side of it and I'll have 90% of the area shaded in. How far along do I need to go? Whereas with the CDF, you'd say, well, where's the 90th percentile? It's up here at 0.9. We'd go across and down to find that same Z-score. So similar strategy. This is the one we're nearly always going to use, but it makes sense just to have a look at this so that we're familiar with it too.